So I'm Kathy, going to be your MC for the day. Here we have Professor Dinkar Sitaram from PESIT, Professor of Computer Sciences, and Ashok Raman, Research Associate from PESIT. Please join me in inviting them on stage to talk on the fishbowl of existence.
Good morning. So thanks very much. It's a great privilege to be here at /N and give a talk to a high-tech company like people from a high-tech company like Flipkart. So what do we mean by the fishbowl of existence? As you know, today with the ubiquity of the internet and networking and mobile phones and so on, there is a lot of data about us which is there on the networks. You know, when you visit a website with online ads, recommendations, teasers, if you're using a smartphone, and of course I don't need to tell you guys about this because Flipkart does a great job of you know, analyzing user transactions and making recommendations, those kind of things. So there have been two reasons why it hasn't been able to do this very accurately in the past. One of them is, of course, the existence of the data itself, and you know that problem has gone away now with the with you know the data mining and you know being able to track every transaction and so on. The second problem, though, is more about what are the algorithms we use. I think we can all agree that if you take a look at many of the things like speech recognition, or you know, human beings are simply much better at recognizing patterns than most computers are. And so the question is, can anything be done about that? Can anything be done about this algorithm part of it? So of course we do have very good algorithms compared to what we had in the past, but still is something even better possible. So that's what I want to talk about today. That is deep neural networks, which is sort of like a kind of recent new technology that allows us to do this mining better. And as I go through the talk, I'll talk about what exactly is different. So let me first talk about what neural networks are. So a neural network is a connection of, it was inspired originally by brains. As you know, our brains consist of neurons and which are connected together in a network. So a neural network is essentially that. There are computational elements which are often called a node or a unit, and then the function has an activation function. So it has a number of, the node has a number of inputs, and then it produces an output. A simple kind of thing is where you know it sums up all the inputs according to the weights which are on the input, and then if that is greater than a threshold, then it fires, and then it of course delivers its output to the next neuron, and otherwise it doesn't. So those are some simple examples of you know, neurons, and the neural network is simply a network of these. And this is, you know, the classic example of a neural network. So you can see the red nodes are the nodes that receive the input, and depending upon some function, they will fire or not fire, and then those will go to the blue nodes, and those again, depending on some function, will fire or not fire, and then they'll produce an output. And this is based, so the simplest and the original one was called the perceptron, which was invented by Frank Rosenblatt, and that was used for many purposes. So once we had these neural networks, the question became, how do you train these neural networks to actually recognize anything, and how do you adjust? So the neural network, essentially, you have all these interconnections, and the behavior of the network depends on the firing of the weights, how you adjust the weights so the network fires or doesn't fire for a particular input. So how do you do that? So this was done by the use of something called back propagation. And so if you look at the neural network, it's a feed-forward network. So here are the inputs. You feed them to these, the first layer is the blue layer, and it will produce some output. And you feed it forward again, this will produce some output. So theoretically, I can use these functions. I can calculate what will be this output given any set of inputs. Let's suppose the actual output is O, and suppose the desired output is D. In other words, I presented this with a face. I wanted it to say 1 or 0, depending on whether it's a face or not. So what it actually says is the output, and the desired output is D. Okay, so what I can do is I can compute the error, and the error can be written as a function of these weights, because I can compute the output depending on the weights given here. And then I can find the derivative of the error, and so what I can do is I can adjust the weights in such a way that the error reduces. So that essentially is called backpropagation. So what happens is I derive the error, I differentiate the error to see what will happen if I change the weights a little bit, and then based on that I can adjust the weights so as to get a better result. So this was the state of neural networks quite some time ago, until say the 1970s or so. So some more background material on the neural networks. So one question is, the neural networks actually didn't turn out to be as successful as people anticipated. I'll mention some interesting properties of these networks. So for example, if all of these functions are linear functions, then the neural network can discover model only objects which are a linear function of the inputs. And you have to have nonlinear functions. And what people found was, through experimentation, that with this classic kind of neural network thing, which is you present some input and then you train the neural network using backpropagation, the accuracy didn't increase very much if you had a lot of hidden layers. So for all practical purposes, if you just had a neural network with an input layer, a hidden layer, and an output layer, that was as good as having multiple layers. And so in practice, that's how people use. They use 3-layer networks, and those didn't turn out to be very good. And the reason for that was that the error, as if you take a look at these remote nodes, the derivative of the error with respect to these weights became less and less, because these are far away from the output. So essentially, that's why three-layer networks is the best. So the problem with neural networks is that you needed a better training method rather than backpropagation, which is not powerful enough to train the network. And so that was the next breakthrough. So now let me take a step back and talk about a little bit of this thing a little more abstract. So what are the things that we would like computers to do if we want them to have human-like intelligence? So for example, if it's search, we may want to be able to, if you take a look at a picture, we may want to be able to search and classify this. We may want to be able to say, okay, this is an auto rickshaw. These are pictures with auto rickshaws, or pattern matching. Similarly, if you look at computers processing speech, you may want them to recognize the speech, and that speech recognition is a very, very difficult thing currently, or classify music, or even identify speakers. And similarly, another thing which would be interesting is in web pages, when you're doing web search, to be able to parse all the sentences, translate them. This can be used for searching, for anti-spam, for machine translation, and so on. So why is it difficult? If you look at it, what a computer sees, if you take a picture of the auto rickshaw, a computer just sees pixels, pixel values. Okay, whereas we see an auto rickshaw or something, right? So there is a fundamental difference between how the computer sees it and how we see it. So if you look at it in a little more detail, so suppose I want to match both of these and find out that this is an auto rickshaw and this is an auto rickshaw. Suppose I try to do it the way the computer does it. I try to do some sort of pixel by pixel matching. So this whole thing is just pixels, and this is also another set of pixels. Then I won't get very far, because for example, the body over here, this is yellowish. This is black and that is yellowish. So there'll be a lot of mismatch, and the shapes are different, the angle is different. Then the computer would come to the conclusion that the second picture is not an auto rickshaw. But there is a second way of doing it, whereby you can actually tell the computer could do better, and it could also distinguish between, for example, a car. And so that is because, for example, suppose I can somehow get the computer to identify a wheel. Okay, so then it can look at this picture and say that this picture has got 3 wheels. This picture also has 3 wheels. You somehow got to infer that the wheel is hidden there. And this one, on the other hand, has 4 wheels. So we could say, okay, this is a auto rickshaw, that's also an auto rickshaw. We can add additional features, like for example, that one, if you look at any car, it has some sort of a grill. There's no grill over here, the grill is a different shape. And so if I look at it, if I do a pixel by pixel comparison, then these all blur together and you can't tell the difference. But on the other hand, if you look at the graph on the right hand side, I can plot how many wheels it has, whether it has a grill and so on. And using that, I can basically figure out that these 2 are auto rickshaws and this is a car. So this thing is called feature extraction. So what I've done is I've taken this picture, instead of being pixel by pixel, I extracted some features like wheels and so on and so forth, and I've used those features in my learning algorithm. Okay, thanks. And this is a general technology which is now used everywhere in computer perception. So I'll have an image, and then from that I'll extract features. So for example, here I'll detect that this has edges over here and those kind of things, and those are connected in a certain way. And then if I have a model of a stapler in terms of how its edges are, I'll have that model over there. Similarly with audio, I'll again get features like, for example, instead of trying to match a word like jack exactly against another word jack, I'll note that there are features, audio features like phonemes like j and so on and so forth, and I will try to match each phoneme which the person has said to the phoneme which is stored in my database, and then I'll identify that these are features. And based on that, I can do speech recognition, I can identify features and so on and so forth. And similarly with text analysis and so on. So what we see is that in the way the human perception works is that I have an input. From the input, I get some features of the input. In the case of, for example, visual things, it could be edges and so on. In the case of speech, it could be phonemes. And then I have some general pattern matching machinery which has a store of all of these features, and then it can detect that a particular set of features is a stapler or it's a sentence or whatever it is. So there is a sort of thing which is specialized to the input, that's the feature extraction, and there's a pattern matching part which is more general. So, anyway, if you look at the traditional machine learning approach so far without the neural nets, then what happens is that there is there are some input which is presented, like for example the auto rickshaw picture, and then some human sits down and decides that, okay, if I want to recognize cars versus auto rickshaw and so on and so forth, then I need to extract these features, like I need to extract wheels, grills, so on and so forth, and then based on that I will do a classifier. So this human aided feature extraction is a bottleneck, because obviously that means that for every domain I need somebody who will sit down and who will extract, say that these are the features I need, and then after that the person would go ahead and then you can build a classifier or train something to do it. So neural nets are interesting and exciting because they remove this part. They remove the necessity for a human being to say, okay, this is a picture and this has wheels, and we can we need to extract views and then we can recognize automobiles. So it removes this part of it. So again, this is more detail about how we would like to do things. So remember I said that we have a sort of generalized pattern matching thing. So what we'd like to do is from the pixels we'd like to do edges, and then we would like to combine the edges and say the edges combine in order to make object parts, and then we match these against in a more general way against different object models. Like you could match these to identify the face, or you could run a similar algorithm. We detect edges at the end, features. These are low level features. These become higher level features, and then those higher level features can be matched against particular objects, or we can match the higher level features to even more general things. For example, I can, I'll have edges, I can match them against, I can match them against, combine these into body parts, then I can say the elephants. And then I'll look at some more elephants and match them again to the higher level features in the chair. And then the highest level feature, which are not shown, could be, okay, I see elephant sitting on a chair, for example. Okay, that could be a conclusion I can come up with. So that's the way human perception works, and that's what it is over here. So basically, I'll have I'll have the input, which is pixels. I combine these to have more features, like for example, wheels, etc., etc. Then this becomes cars. This is a higher level feature. I can combine the wheels and so on into cars. And then this is the highest level where I look at a video and say, okay, there are multiple cars, or there are cars in an accident, or one car is trying to overtake another, and so on and so forth. So these are really great that we are saying that we want to look at some input and then get an output from it. We want it to be able to extract features without training it, without explicitly saying these are the features to look for. So how do we do it? So this has been done with something called a restricted Boltzmann machine. And the concept of a restricted Boltzmann machine actually dates back to the 1960s or 70s. But the restricted Boltzmann machines were very difficult to train. And so what happened is that recently there had been algorithmic breakthroughs in how to train these machines. And so that is why there has been a renewed interest in neural nets. And the restricted Boltzmann machine is one approach which makes it very easy and possible. So I won't go into the mathematics of it, but the restricted Boltzmann machine has two layers. One layer is the visible units, and another layer is the hidden units. And the thing about what makes the restricted Boltzmann machine is there are no connections between the hidden units. The hidden units are connected only to the visible units, and the visible units are connected only to the hidden units. So these are called visible units because this is where the input comes in. So they are sort of visible to the outside world, whereas these are not visible to the outside world. These are called restricted Boltzmann machines, and it turns out that you can calculate. Suppose the input is 1, 0, 1. I'm just making this up. You can calculate, and the hidden units could be either on or off. They could be 0 or 1. Okay. You can calculate the probability of Boltzmann machines are the property that you can calculate. Suppose this is 1, 0, 1. And this is 0, 0, 0, 1. You can calculate the probability that this is 1, 0, 1 given that this is 0, 0, 0, 1. So these are again neural nets. So the input comes over here, and then these neurons fire or don't fire, and based on that these also have some output. So you might wonder where this probability comes in. So this comes in from a biologically inspired phenomenon. And so again, these neural nets are similar to the way the brain works, but not exactly identical. So to motivate why this has a probability, let me give an example. I mean, suppose this is a neural network, I mean actual set of neurons in the brain. If you inject some chemicals, let's say 101, so you inject the chemical here, you don't inject the chemical here, you inject the chemical here, then the chemicals will diffuse along these neural paths, and there will be some concentrations of chemicals over here. So based on statistical mechanics, that is the way the thing diffuses, you can say that if there is a certain concentration of chemicals here, what is the probability of the concentration of chemicals here? Because it's a statistical diffusion process, so it isn't exact. So conversely, since you can calculate the probability of the concentration here given this, you can also do the reverse. If you are given this, you can figure out what's the probability that there is a certain concentration over here. So that's how restricted Boltzmann machines work. So you give an input over here, and you calculate what is the value of the hidden units such that this probability of the visible unit given the hidden units is maximized. And if I have a training set, then I simply maximize the product of this. So as you can see, this is a fairly complex algorithm, and the real breakthrough which occurred recently in about the 2000s was an efficient way of calculating this the value of the weights for the hidden units in the Boltzmann machine. So it turns out that restricted Boltzmann machines can do what we had said, that okay, if you give it a feature like a car in terms of pixels, then it will generate one level of features like wheels, for example, and we don't know what it will generate, and another level of features, and so on and so forth. And as you have more layers, so this is the input, it will generate one layer of features, low level features like wheels and so on, another layer of features like cars, and then if you have multiple cars, it can generalize to more layers. So what happens is, so the interesting thing about this is, which is a difference from the traditional neural nets and the traditional machine learning algorithms, is that nobody told the neural net that here is a picture of an auto rickshaw, you have to look for wheels and grills and so on. With the restricted Boltzmann unit, which is kind of based on the way our brain works, the neural net, which is a simplified model, it also somehow does the same thing. So when you give an input over here of an auto rickshaw, it might, or multiple auto rickshaws, it might extract wheels as a feature and so on and so forth. So that's the interesting thing about restricted Boltzmann machines, that it keeps on giving higher and higher levels of abstraction. So that's essentially the base, the core of the talk. So basically, if you look at the earlier machine learning systems, even though they are very good, one bottleneck is you have to tell them what features to look for when you're given an input. And there's a lot of expertise has been done on this, but this of course limits the scope and capability of machine learning systems, because somebody has to tell the machine learning system what to look for. It doesn't automatically generate its own template, and time consuming, very likely incomplete. So if you program a traditional machine learning algorithm for a certain set of features, because you want to say distinguish between cars and auto rickshaws, it may not work very well when distinguishing, say, cars and bicycles or something else, or different kinds of cars. So that's because when the expert extracts the features, he would do it only for a particular set of features, which he thinks is relevant for distinguishing between cars and auto rickshaws. So if you want to distinguish between different set of cars, it may not be very good at that. With the neural networks, you can get most information in an unsupervised fashion. So this is the way, this is at least the promise of how neural networks can work. You feed in the picture over here, or a better example, you feed in a sentence, a small crowd quietly entered the historic church. So it breaks it up into one phrase, another phrase, and then puts it into a sentence. And you can have a higher level of abstraction whereby it has a knowledge base. As many of you know, Christians go to church on Sunday. So it might say that, okay, there's a high probability that the day is Sunday, and it's able to generalize and so on. And if you take a look at it, this is again very similar to the way human beings generalize here. So, we learn by looking at objects and learning how to recognize them. And this is one difference between the traditional neural networks and and other kind of machine learning techniques, in that people say that neural networks are a generative model. So when you keep on feeding pictures of things like cars, automobiles, it just learns the various features. It doesn't learn how to distinguish between a car and automobile. But just like humans, it learns that this is a car, this is an automobile, etc., etc. And then later on, you can train it to tell the difference. So it has a sort of so what the neural net does is a general purpose thing. It's not trained for a particular purpose. It's trained to just recognize various objects. And then once you recognize various objects, then you can have more complicated tasks, like is this a car, is this an auto rickshaw, or is this what kind of cars these are, etc. So this is just a summary of what we said so on. And this deep learning is one of the hottest topics in research today. There's a lot of work going on in deep learning in speech recognition. So there are IBM, Microsoft, Google, they have deployed deep learning based speech recognition systems in the products, which they've shown are much better than other products. Again, in computer vision, again Google has done a lot of work in this. And there are a lot of areas in which it works: image classification, video surveillance, analyzing video and annotating video, and so on and so forth.
So I'm Ashok Raman. Just to this something else. So the whole idea was I wanted to bring the discussion back to where we started, right? Where Professor Dinkar started. What we had, this is good enough, right? Okay. Yeah. So what we are saying now is that all along there have been pockets of machine learning. There have been identifications in object detection. There's a lot of algorithm, a lot of work going on. There is a lot of work going on in text area. Identifying text, identifying even moods and semantics and sentiments in text. And of course, motion detection and things like that. But now all of that potentially, because of our increased processing power and the increased environment, I mean the ubiquitous Hadoop, what was the InMobi guy saying, some 160 million Hadoop jobs kind of a thing. So you're coming to a point where this multi-modal situation where we can actually derive intelligence from these various other inputs. So I can take semantics from text into a video and say that these guys are going to church because it's Sunday, and that Sunday information is nowhere in the picture, right? So if you as Flipkart, want some of that intelligence to come in based on his last browser sessions or his last location, right? So the location information is coming in, his last purchases are coming in. So all these things are putting together so much information about you that you have no idea about. And that's where we wanted to tie into being you being in a fishbowl, wherein the approach of neural networks is becoming so critical. Knowledge representation, as Professor Dinkar was saying, has gone very deep at one point, and now is getting slowly abstracted into higher levels of just sufficient information from a picture, from a series of how do I maintain that video to give me just enough information in terms of images as well as maybe temporal, that if a car comes into a PESIT campus without headlights at night is a dangerous situation. So I need the temporal information maintained. So this abstraction of information to this level is what neural networks is very good about. So neural networks has these features extracted, saying I just don't need the image, I just don't need the various shades of the color, I just don't need the fact that the headlights are on or off. I also need the time information, and with this I can come to a certain conclusion that I have never been able to do. And that is what we are trying to say, that as we can do various far more classifications of the information based on having all these things together in one a huge information base, wherein I can come up with a late fusion of this information to come with very final decisions of classifications of the behavior of or the intent in terms of physical action. And if that happens at real time, then you can even possibly predict that there is a mob gathering, and then, or there is a sequence of things, a pile-up has already happened. Now that information, or it can potentially escalate to a fire or whatever, those kinds of situations, again based on your learning algorithms that are already there. So based on weightage, based on information, based on each of these, what Professor Dinkar was saying, hidden nodes, with the hidden nodes getting smarter and smarter and having increased processing, you are coming up with newer decisions. And some of them are obviously wrong, which is why we get into pruning of some of these, which is an inherent system in neural networks. So, which is why the next age of neural networks is far more promising, and the RBM algorithm that Professor Dinkar was saying, there's a lot more research work going on there. I can do a quick demo if somebody is interested, but our demo is very disparate. At PESIT we are doing some object detection. Again, we are trying to reach that area where all these things can come together. So there is a group that's doing speech processing, there's a lot of work going on in speech recognition, accent recognition, and then there is work going on in object detection, and then finding behavior patterns. Now, if all that comes together, then we are looking at, again, text engineering in terms of semantics, right? So if we can get all of those things together, and of course, like the morning talk, the Flipkart approach of, crowdsourcing, bringing in open source tools to bring all these technologies in an integrated fashion to come up with some final decision, and that's what we are working on. I can quickly run through trouble is like, okay. This is kind of a market predictor model. Basically, based on Yahoo stock information of the past, it actually runs through and predicts what the future should be based on the weights, based on the typical curve fitting kind of a situation, right? And then it learns and says that I predicted this, and my actual numbers were up and down, were so far out, right? So potentially, if you just looked at just pure, that feature is just the day's highs, lows, or closing numbers of the stock. But if you brought in something else, saying, Apple has released a new phone or something like that, and therefore potentially the stock could go, that information also will have to be built in. And that is the kind of additional semantics that we need to add in to make the neural network really deep. And that is the depth that we are trying to work at. We are also using a tool called NCOG that I can run you through an object detection thing that our friends are working on, our colleagues. So they are looking at that larger white car, and they are tracking it's been digitized to frames, and they are tracking the car movement. And what we are picking up is building a model that says when the car is visible and when the car is not visible, and extracting those coordinates. And of course, the timing has to be maintained also. So once the timing is maintained, and assuming the car is there, and then we have to get into finer details of the wheels or any other information we need about the car. And this is again not entirely PESIT work, but we are going ahead and working on it from open source and adding our piece to it. And we want to integrate this with kind of a typical neural network information. And not here. That's what I'm saying. So we need this model to be that's one piece of the puzzle. So now I need the temporal data that need not always be there, and then I need any other semantics that I need to add with it. So this is just pure object detection. So that's why I said we are working in pockets in these areas. And now we are looking at how best to we are looking at how best to integrate this to come up with some more intelligence. Sure.
See, in terms of deep learning, one of my colleagues was experimenting with deep learning. So one of the problems he's facing is like the training. I mean, he's training I think 200 to 200 size images.
Right.
He has a few hundreds of them. So it's on a fairly high. It's on a fairly high-end GPU. But still, it's taking like forever. And the thing is, and the neural net. I mean, it's a recurrent neural net, convolutional. So the thing is, the nature is such that you can't really. It's not really a map reducible problem because easily at least, and you don't really get much map reduce benefits because it's a lot of optimization happening. So as an iterative program, so which again map reduce is not very this thing for it.
Yeah.
So how, from your experiences, like how long does it take to train in deep learning networks?
Yeah, I can relate to that. My only take to that is we are working with higher margins of error right now. What we are saying is if it is approximation, and this is where the deep learning comes in. I mean, there's a likelihood we'll be making mistakes. There's a likelihood that one edge of a tree gets mapped to an edge of a river and the weightage is still significant, and some human interaction has to come in to reduce that weightage to something else, right? But we have to work with a larger error rate, which means some of these mistakes can happen. But the whole idea is we want to at least get a framework in place before even we think in terms of going across higher GPUs, processing powers, or identify certain modules that we can replicate in terms of this Hadoop. Yeah, I mean, what can we do independently without interrelationships? The neural networks that Professor Dinkar said, each of these nodes can actually now, in the traditional manner, were all feed forward and would not interconnect. They would not communicate to each other. The information, this morning he was talking about dynamic programming, right? The thrust of the dynamic programming is that if you have a piece of information that you already know, you better hand it off to your next colleague so that he can take off from there. And that becomes important insight to getting rid of some of these errors. And so if we can bring in something like a dynamic programming to improve reduce some of these iterations, right? That's a possibility. But again, those are, so this whole area has suddenly exploded in terms of research and interest. They call it a recurrent learning, wherein some of it is iterative, but some of this information that comes from the top is actually handed off to the bottom. So a bit of extra information, like again in the genetic example in the morning, he was bringing in the experts, I thought, very late. He said after we had reduced the sample size to so much, the expert could now look at the data. But if the experts had given in some more of the weightages, saying that if this is a I'm not a biologist, if this had a genetic disease and this could affect so many other patterns, right? That information would have reduced his search dramatically. And if you could bring in that kind of an information early on, which comes, as a hindsight, and which is exactly reflected in the way we work. Some of our learnings comes from hindsight, and then we use that for newer situations. And that is exactly what neural networks is trying to mimic. I know I went off in another tangent, but yeah, this is the thing. We are not looking at performance straight off right now. We are just trying to functionally, we are functionally working it so that we can bring in as much information back to see if it works.
So if I can add to that, I think the Jeffrey Dean paper talks about how they reduce the size of the image by sampling it and finding representative pixels. And we are also kind of experimenting with that in our image detection kind of thing. Because it does take, even for smaller images, as you say, a very long time to run. And so has your friend tried that? I think that probably would be the thing to try.
Excuse me. Hello. So as Professor Dinkar was saying, in restricted Boltzmann machine, we don't need manual intervention to extract features. So is this like completely, we can just give any data set to the machine and it can classify, or does it also need some training data? And
Yeah, so I think I simplified it a little bit. There is more architecture thing in terms of, for example, the restricted Boltzmann machine has a transfer function, output versus the input. And then there are features such as, as I said, in image sampling the image, if the number of pixels turns out to work well. And the other thing is that in various other situations, for example, there's a concept known as pooling, whereby you can feed every input to every output. But pooling, for example, if you're looking at image, then you feed each input only to adjacent pixels, and so on. So the restricted Boltzmann machines, I think, what it does is it allows you to come up with a neural net for each domain, as opposed to the earlier kind of machine learning, where you have to come up with algorithms not only for each domain, but also for the feature that you want to recognize. Because
it does it by training.
yes. So there are various architectural alternatives, like, should like as I said, pooling and so on, so the sampling the pixels in the case of the image and so on. So there are various considerations for designing the machine. Excuse me. But the thing is, once you design the machine for, say, recognizing images, then it can do a lot of things on images. You don't have to train it for recognizing a particular kind of images. So.
Thank you.
How is the feature detection happen? Because there might be some noise always in the test case. So my learning set might be proper for a proper image. Like it can be because I'm giving a proper image for every car or auto, but my learning set can be or my testing set might be having some kind of noise, or there might be an angle difference. So how am I doing the feature extraction here?
Yeah, noise is always there, right? I mean, we have worked with again several tools, especially in speech recognition, to get rid of noise fairly easily. Yeah, that's a fairly well-known problem actually. But like we said, the feature extraction itself has taken a different approach in terms of coming to conclusions based on higher level, like we said, edges, right? Edges is one way of identifying that there is possibly a wheel, and then coming to conclusion that it's a wheel, right? It could be an edge of a river bank to a landmass to a path or something like that, right? So how do I, and some of these maybe, how do I distinguish a sky from a river? Say maybe they are all blue in color. So if you add the blue element and the edge element, and so some of that will have to be done humanly. You will have to improve your training data to a point where even with something like as simplistic as edge detection, you want to add some more information for it to now know that, no, this is a piece of lake or a river and not the sky, right? So that level of feature extraction input has to be done. So that level of supervision, as we call it, has to be done.
So it can be done based on kind of dimensions or the body structure Is
Right.
it?
I mean, so the sky can be on the top, so and the river at the bottom. I mean, the lower part of the picture, kind of a thing. So that has to happen. Otherwise, you're losing out on that information that helps you come up to these conclusions. But the point is, you're still not maintaining the entire set of every pixel, every value that people were struggling with. People were writing algorithms for years to come up with these kinds of distinctions before. But now that has considerably reduced. They completely changed from, looking at these things from the way we perceive it. That means we see a silhouette and then we assume it's a person very quickly. And working with the silhouettes is enough for us to know that this guy is there and therefore that information is enough for us to take the next level of decisions and the next level of judgments.
So my question was related to that, right? You could bias the output based on too much information.
Exactly.
And so the wrong inference could be derived based on too much input.
Yeah,
which means
and
that
too
it
much
would not
training
be.
itself could create problems. Yes,
So-
that is
So what could be an error in one context, maybe a correct answer in a
correct
different
answer.
context. So
Absolutely.
it would all be context
Yeah,
sensitive in that
that's-
sense.
yeah, I mean, they used to say the curse of dimensionality, right? You had too much information and now we are reducing it, and maybe you are reducing it too much. You are looking at it in one angle. Yeah, so that problem is there.
Guys, any more questions? You can personally interact with Professor Dinkar and Ashok Raman. Thank you so much, Professor Dinkar and Ashok Raman. Thank you so much. I think you can.